Okay, so we're going to jump into it. So again, tonight we're going to do a review session for your multiple choice exam on Friday, which is on chapters 11, which is our solution chapter, and chapter 12, which is our rate chapter. Now, if you weren't here on Monday, I did provide a bunch of challenge problems, but on Monday we covered chapter 13, equilibrium, which is not on this exam. And so I'm not going over the challenge problems from Monday, okay? There's only one that we're gonna go over, and it was actually a challenge problem from last Wednesday that I had to make a small correction to on Monday, right? So this is the only challenge problem given on Monday that we're going over, and it actually is a chapter 12 problem, and definitely one you should be familiar with. I would say we'll definitely be familiar with it. I would anticipate a question like this more on your long answer, but they definitely could make it into a multiple choice question. So hopefully going over this will make this problem, which is a really tough problem, a little bit more digestible for you. Okay, and so we're told that we have a first order reaction that has a single reactant and it's run at 27 degrees Celsius with and without a catalyst. Now you're told that when you run this without a catalyst, your rate constant is 0.46, right? That's the number I had to edit. If you did 1.46, it wouldn't have worked. So I'm sorry about that. Okay, and then you again ran it at 27 degrees Celsius still, this time with a catalyst, and found that the rate constant is equal to when you run the reaction without a catalyst at 62 degrees Celsius. Okay, and it basically asks how much faster does the reaction with the catalyst go? And then this statement at the bottom is typically what you'll see in a catalysis problem like this. It says the frequency factor A is the same for both reactions. Okay, and again, you'll see that pretty much in every catalysis question, at least any that the professors have brought up in the last couple of years. And the reason for this is this statement allows you to assume that A is 1, right? You can just say my frequency factor is going to be 1. And when you take the natural log of 1, it's equal to 0. Okay, so this statement almost allows you to ignore your frequency factor altogether. Okay, and so this one, I tried to write out my solution to kind of really step-by-step work through my thought process, right? So a lot of information is given at once in this problem. And so I always say that if you don't know where to start, just write down what you know. Okay, so not only did I write down what I knew and what I didn't know, I had also written down the equations that I thought might be important for this problem, right? So the first equation is our Arrhenius equation. I've just taken the natural log of the entire thing, right? This is the form you'll probably be more accustomed to using. And then I wrote down that CC equation that allows us to evaluate at 2 different temperatures with 2 different rate constants. Okay, now our activation energy for our catalyzed and uncatalyzed reactions are both unknown. And then we're looking at 2 different temperatures, right? Temperature 1, I'm going to call 27 degrees Celsius, which is at 300 Kelvin. And our second temperature is 62 degrees Celsius, which is at 335 Kelvin. Okay, the last pieces of information that I know is that K1, which is our rate constant of the uncatalyzed reaction at 27 degrees Celsius, is equal to 0.46. Okay, and then K2, which is the rate constant for our uncatalyzed reaction at 62 degrees Celsius. Well, we don't know the value of that, but we know that it's equal to K3, which is the rate constant of our catalyzed reaction at 27 degrees Celsius. Okay, so we don't have a value for these, but we know that they're equal. Okay, and so I actually just start with that CC equation, right? And so I plug in my K2 and my K1, which are my rate constants of my uncatalyzed reactions at 62 and 25 degrees Celsius, respectively. Okay, and I picked these 2 K values because they're both uncatalyzed, okay? And that's just important when we get to the other side of the equation, right? On the other side of the equation, we have activation energy. Now realize that our activation energy will be different for the uncatalyzed reaction and for the catalyzed reaction. Okay, and so this entire equation here is for the uncatalyzed reaction, which is why I used K values that correspond to the uncatalyzed reaction and my activation energy in terms of my uncatalyzed reaction. Okay, that activation energy is going to be divided by R, and then it's multiplied by 1 over T2, which is the temperature associated with the top number, minus 1 over T1, which is associated with the bottom K value. Okay, and I know that the equation in the equation sheet might be slightly different. The reason for that is this negative sign that I use, but this is always the general format that I personally use, and so I would just say stay consistent, right? Your equation sheet has a slightly different equation, but it will get you the same result every time, okay? And so from here, I start plugging in my values, and I quickly find that I actually have too many unknowns, right? I don't know this K2 value, but I also don't know what the activation energy of my uncatalyzed reaction would be. Okay, and so I know that in order for me to solve for my K2, I have to first find my activation energy. And I can do that using the derivative of this Arrhenius equation, right? Taking the natural log of the entire thing. Okay, and what I'm gonna do to this equation is input my values from my uncatalyzed reaction at 25 degrees Celsius, right? So my K, my rate constant for the uncatalyzed reaction at 25 degrees Celsius is 0.46, right? That statement at the end of the prompt that says that the frequency factor is the same for all reactions allows me to assume that it is 1, right? So ln of 1, and then minus activation energy over R times T, right? So all this information is for our uncatalyzed reaction at 25 degrees Celsius. So the temperature I'm going to use here is 300 Kelvin, right? Which is just I'm sorry, that's supposed to say 27 degrees Celsius. I'm sorry, which is 300 Kelvin. And then my R value is not my ideal gas law constant R, but rather this 8.31 value, right? And when I solve for this, I find that the activation energy of my uncatalyzed reaction is about 1,936 joules. Okay, and so I'm going to go back and plug it up into this CC equation up here where I didn't have that value before. Right, so I just plugged in all my numbers. Again, this is the CC equation that we already had, but we just solved for activation energy, and we are still are looking for K2. Okay, and so all I do is solve the right side of the equation, and I find that the natural log of K2 divided by K1, which is this 0.46 value, is equal to 0.0811. Now remember that the rate constant of our uncatalyzed reaction at 67 degrees Celsius or whatever, 60 something degrees Celsius, and our catalyzed reaction at 27 degrees Celsius, they're the same. Okay, so I'm just going to substitute K2 for K3 here because, again, they're equivalent in value. Okay, and they actually asked me not to solve for what K3 is here, but they ask how much faster does the catalyzed reaction at 25 or 27 degrees Celsius, how much faster is it than the uncatalyzed reaction? And so what they're actually asking for here is the ratio between K3 and K1. Okay, and so all I have to do is get rid of the natural log, which I do by doing e raised to this power. So it's e raised to the 0.0811. And I find that this ratio, K3 divided by K1, is about 1.08, meaning my catalyzed reaction goes 1.08 times faster than my uncatalyzed reaction at 27 degrees Celsius. I know on this I wrote 25. I apologize. I just use that value a lot. But wherever I write 25, I meant 27 degrees Celsius. Are there any questions on this problem? I know there's a lot of steps. Just a minute in case any questions arise. Okay. Well, before going into the review portion, there's just one other thing that I want to cover, and I think I promised to go over this again maybe last Wednesday or even last Monday, right? So I'd given one of these problems, which is one of the novel synthesis problems, right? Where you actually don't have the information really to solve for all of the orders of each reactant, right? Typically, our process is to find a trial where only one reactant changes in concentration and see its effect on reaction rate. Okay, so for this problem, we actually have 3 reactants, which made it a little extra difficult, right? But we can solve for the order of reactant B by using trials 1 and 2, right? Because the concentration of A is the same, the concentration of C is the same, and only the concentration of B changes. Okay, and so this change in concentration of B directly causes the change in rate that we see. Okay, so we can do that ratio and find the reaction order of reactant B. Okay, we can do the same thing for reactant A by using trials, I believe it's trials 2 and 3. Yep, in trials 2 and 3, right, the concentration of B and C stay the same, while only the concentration of A changes, right? So whatever change in concentration A causes, or sorry, whatever change in rate caused by the increase in concentration of A is attributed to it, right? So this is kind of just our generic way of solving for it. Hopefully by now you're all used to this. And so we find through our data with the experiments I said that the reaction order of reactant A is second order, and the reaction order of, the order of reactant B is 4. Okay, but how about reactant C? So let's go back to the data. So looking at the 4 trials we are given, right, we can't pick any 2 trials where the concentration of C changes, but the concentration of our other reactants does not change, right? There's no easy way to do this. Now, the typical way to kind of circumvent this problem is to create a new or novel trial experiment, right? We would make trial 5 with its own data to solve for C. Okay, and so these are the general steps that we take to do so. Okay, so the first step, it's kind of a pre-step, is use the normal process to solve for the order of as many reactants as possible, right? We just did that for A and B. And these steps are typically, this is for when there's only 2 reactants. So in this case, it's a little bit harder. But these are the general steps that can help you solve for the reaction order of what in this case is C. Okay, so we're going to start out by choosing a trial, right? We're just going to choose a trial to start with. And typically we want the concentrations of our reactants to be pretty small. Okay, so step 1, choose a trial. Step 2 is identify a trial where our concentrations differ from the concentrations in the trial that we chose in step 1. Okay, so the trials that you choose in step 1 and step 2 should have different concentrations. Okay, and then what you're going to do in step 3 is you're going to take the compound that you know the reaction order of, and you're going to change it so that it matches the concentration of the trial that you picked in step 2. While the concentration of the reactant you don't know the reaction order of, you're going to keep the same. Okay, and then from here, you can kind of evaluate what the reaction rate for this novel trial should be, and then you can use that trial and a previous trial to solve for the reaction order of the unknown reactant. Okay, and so this is how I did it the first time while in SI, right? I chose as my step 1 trial was trial 2, right? And here's the data for it. My step 2 trial, right? I wanted the concentrations of my reactants to change, okay? But I initially in SI said that we wanted only one of our reactants that we know the reaction order to change, right? So in step 2, my trial, I wanted to keep the concentration of B the same. I wanted concentration of A to change, and I wanted the concentration of C to change, okay, when comparing trials 2 and 4, right? So I wanted concentrations of A and C to change, but B to stay the same. Now I made my new trial by changing my concentration of A from trial 2 and by keeping from trial 2 my concentration of C exactly the same. Okay, so when we compare trial 2 and our new trial, right, only the concentration of A is changing. And we can see that the concentration of A changes by 3 times. It's tripled. And we found out earlier that A is second order, which if A is second order and it tripled, that means our reaction rate should become 9 times what it was. Okay, so we can find the rate of this new trial by doing 9 times our rate in trial 2. So that's how I got this value. Next, what I would do is take trial 4 and our new trial to do the same setup we were doing before to evaluate what the order of reactant C is, right? And we pick these two trials because the concentration of A and B stay the same and only C changes. Okay, so this is a completely valid way of doing it. I just wanted to show you that there are actually 2 other ways to do it. Okay, so notice here when I picked my step 1 and step 2 trials, right? I wanted C to be different, I wanted A to be different, but I purposefully made reactant B's concentration the same, right? I picked 2 trials where that didn't change. Well, let's try it again. And here I'm going to use my step 1. If you kind of look at my steps to solve these, my step 1 reaction that I picked was trial 1. My step 2 trial was, again, trial 4. And that's what I use. Okay, and so when making my new trial, I'm going to change my concentration of A from trial 1, and I'm going to change it so it matches the concentration of trial 4. And I'm going to do the same exact thing for concentration of B, right? I change it from the trial 1 concentration to match the concentration in trial 4, okay? But C, which is my reactant that we don't know the reaction order for, that concentration I have to keep the same, okay? That has to stay the same, okay? And so when seeing the difference between trial 1 and our new trial, right, our concentration of A tripled, right? And it's, again, A is second order, which means if it was tripled and it's second order, then my new rate should increase by a factor of 9 due to the concentration of A. But not just A changed this time. This time, the concentration of B also changed, okay? And my concentration of B increased by 3.5 times what it was. And B as a reactant was fourth order in nature, which means when we see this 3.5 increase, the rate of my reaction should increase by 3.5 times to the 4th power, which basically makes the rate about 150 times faster than it was before. Okay, and so to find the rate of my new trial, I'm going to take the rate from trial 1 that I had and multiply it by 9, because that's how much faster reactant A makes it. And I'm going to also multiply it by 3.5 raised to the 4th, which is how much faster reactant B is going to make it. When I solve this, I find that the reaction rate of my new trial should be 7.124 times 10 to the negative 5th. To solve for the order of C, I again take my new experiment and my trial 4, and I plug that data in, and again, I solve that the reaction order of C is 1, right? So as you can see, these 2 slightly different methods give me the same result. Now there's one more way that actually, thank you very much to, I know she's not here right now, but a student actually emailed me asking if this next method was a way to do it. And I've actually never seen it done in this method before. And so if you like this method, I would definitely encourage you to go back and try some of these practice problems using this method to truly evaluate that it works. But from looking at it today, I do believe it should work every time. I know somebody just sent a question in, and I will go through this and then I'll kind of answer all questions relating to this topic at the same time. Right, and so for this third method, right, I just wanted to remind us that reactant A is second order, reactant B is fourth order, and for this method, you can use any trials. okay, as long as your concentration of C is not the same. Okay, so I use trial 3 and 4 for this method, but you could have done trial 1, 2, or 3 with trial 4. Okay, one of your trials had to be 4 in order for your concentration of C to change, but you could have done trial 1, 2, or 3 with trial 4. Okay, and so all I did was input all the data from these, right? So this is just what was in the chart. And what you do down here is you actually do what we've been doing before, but for all of our reactants, right? So I'm going to put all of our trial 4 data in the numerator and all of our trial 3 data in the denominator. And what I basically do is I do the concentration of A in trial 4 divided by trial 3 raised to its reaction order, which we know A is second order. We're going to multiply this by the ratio of B in trial 4 and 3 raised to its respective reaction order times the concentration from trial 4 and 3 of reactant C raised to its reaction order. And this is equal to, again, our ratio, just like before, of our rate of trial 4 divided by trial 3. Okay, and so basically when you do this math, it comes out to about 0.62. This is the effective, the change in concentration of A, times 1, which is from reactant B, times basically the ratio of C raised to its reaction order. And when you go through this and solve for the reaction order of C, you find that, again, it's 1. And what I want to point out to you here is this is actually the method that we use almost every time, right? But think about what we typically do to solve these problems. Typically, we want the concentrations of all of our reactants besides one to be the same, right? And so in this case, B is the same. And when we do that ratio, it comes out to 1, right? So if we go back to when we solve this, solve for the concentration of A, or sorry, for the reaction order of A based on the concentrations, right? B and C are actually being factored in here. But when we solve for this, we use 2 experiments where the concentration of B and C didn't change. So when you do that division and raise it to its reactant order, it's just 1. Okay, so this method that we do in the third attempt to solve it, the third different method of solving it, this is actually the same exact method that we use every time. It's just that when we do this ratio of other reactants, it's not always necessarily 1. Okay, if there are any questions on these, I'm happy to answer them now. Yes, so Amanda, you're correct. Right, so this is another way to do it. This actually circumvents the need to make a novel trial. One thing I would say is when they've taught this in the past, they have asked students to make a novel trial, a new trial. So I would suggest that everybody before both exams on chapter 12 at least understand how to make a new trial. Okay, this one's harder because it has 3 reactants, but I would definitely recommend everybody at least understand this and know how to do it. But if you like this method better, more likely than not, you'd be able to solve it this way. Just in case they ask for some weird, maybe what's the data of a new trial? I don't know. I don't think they would ask that, but just in case. Okay, going back to answer questions. Yes. So again, if your TA has reviewed it, I've never seen this method before. Now that I've seen it, I love this method, this third method that we use to solve it. But again, just in case a situation comes up where you actually need to be able to make that novel trial, understand the process, the first 2 that we did, or the first method of solving this. Okay. If there are any questions, I'm happy to answer them. And if there aren't, if you don't mind just signing in right now using your net ID, and that'll kind of indicate to me that there are no questions before we go through a little review of all these chapters. or both of them. Okay, and so as people are asking questions or signing in, I'm just going to talk very briefly about the challenge problems tonight. So tonight I'll be giving out 15 challenge problems. 13 of them are multiple choice. The last two, when I try to make multiple choice questions, I try to purposefully pick answers that if you make one wrong step, kind of cause you to get that other answer. But for the last two, I kind of struggled to come up with real options. So I left them as long answer questions. There'll be 15 of them, and I'll make an extra video tonight going over those with explanations. But I won't be releasing them until that video comes out. I think I just need to validify 3 of the problems, 3 or 4, just solve them out, make sure that they come to the answer, make sure I gave you all the information you guys need. And so just because I haven't been able to go through that last check of them, I'm not going to release them during this session, but I'll, in my next session that I'm just recording and uploading tonight, I'll make sure that I go through all of them before solving them out. But again, I'm trying to avoid sending problems out and then needing to make a couple edits. I'm trying to avoid that. Okay, so let's go through chapter 11, which is our solution chapter. And so this review is going to seem relatively similar. I didn't really change much from the last review of it we did. And so just to remind you of our 2 components of solutions, right? There's the solute, which is the portion that gets dissolved. It's almost always present in smaller or lesser amounts. And in this course, it is almost always a solid, okay? Our solutes are almost always solids, but especially with this exam being a multiple choice exam, I would definitely note that our solute can be in any phase, right? You can have a solute that's a gas. You can have a solute that's a liquid along with a solid, okay? So just keep that in the back of your head. It's almost always a solid in this course, but it has the potential to be in any state, okay? And same thing goes for solvent, right? Solvents in this course are pretty much always a liquid. Specifically, they're almost always water, okay? But a solvent can really be gas, liquid, or solid, okay? And we define the solvent as the portion that does the dissolving, and it's normally in greater amounts, right? So these 2 are our 2 components, meaning when we add their mass percents together or their mole fractions together, they should equal 100% if you're talking about mass percent or a mole fraction of 1. Okay, and we have 4 main solution compositions that we learned. Normality is in here. I don't know if they'll talk about it. I actually made a practice problem tonight just to kind of make sure you're not forgetting about it. But the main 4 are the first 4 I've listed. Okay, so there's molarity, which we're very familiar with by now. It's denoted with a big M, and it's moles of solute divided by liters of solution, right? Then we have mass percent, which is it's the mass of whatever component you're talking about divided by the total mass, and then we multiply it by 100 just to turn it into a percentage, right? We have mole fraction, which we denote with an X, and the mole fraction is moles of the component in question divided by the total moles, right? Mole fraction will always be a decimal. You should never have a mole fraction above 1. It's just not possible. And our other big one is molality. And be very careful. Molarity is the big M. Molality is the little m. Okay, and molality has the same numerator as molarity. It's moles of solute, but it's the denominator that is different, right? It's kilograms, but it's also kilograms of just our solvent, right? It's not molarity is in terms of solution. Molality is kilograms, but kilograms of solvent. Okay. And then again, there is normality. So normality is extremely similar to molarity, okay? But it's moles of important portion over liters of solution, okay? And so you'll see this in acid and bases a lot, right? So a 0.1 molar solution of sulfuric acid, H2SO4, is, if it's 0.1 molar sulfuric acid, it's 0.2 molar H plus, and so you might just see it labeled as 0.2 normal sulfuric acid, right? It's just saying that the H plus portion, the portion we care about, has a concentration of 0.2 moles per liter. Okay, and so I don't really expect you to see normality, but if you do, it'll probably come up in terms of acids and bases. I can tell you that that's really the only place I've seen it. But we do have chemicals in the lab that are in terms of normality. Okay, and so oftentimes in this course, you'll have to interconvert between these measures of concentration, right? You might have a multiple choice question that asks you to do this directly, or in our colligative properties, when you need to use molality, they'll give you the molarity, or vice versa, right? So you'll either directly or indirectly need to do these interconversions. Now, to help facilitate the easiest interconversion of these measures of concentration, we recommend you use these assumptions, right? If you use other assumptions, you'll still get the answer. It's just your math will be harder, right? So if you're trying to convert from molarity to any other unit of concentration, your calculations will be easiest if you assume you just have 1 liter of solution, right? If you're starting with mass percent, it's easiest to assume you have 100 grams of compound, or in this case, it'll be 100 grams of solution. Mole fraction, it's easiest to assume you have 1 mole, and molarity, this is molality, so you have to be really careful with it. Molality, it's easiest to assume you have 1 kilogram of solvent. If you're asking where's normality on this, if you have normality, you should make the same assumption as if you have molarity, okay? So if you're given a normality, assume you have 1 liter of solution, and that'll make, again, it'll just make your calculations the easiest. If you want to assume that you have 55.57 liters of solution and do your calculations based on that, go for it. Again, it's just going to be a little bit more challenging to do the conversions. Okay, we also have 3 main factors that affect solubility, and these are definitely things that I would expect to see to some extent on a multiple choice exam, like almost 100%. I would definitely bet some money that at least one question will have to do with solubility. And so the first factor is just kind of a characteristic of compounds, which is like dissolves like, right? So polar solvents will dissolve polar molecules, right? And remember, polar molecules are made of non-metals, and they have polar bonds, but make sure you're checking their geometry. That's very, very important. Okay, so polar molecules and ionic compounds, right? So remember, ionic compounds are between metals and non-metals. Okay, so those will dissolve in polar solvents, while non-polar solvents will dissolve non-polar molecules. Okay, now our second factor that affects solubility is pressure. And so as pressure of a gas increases, the solubility of it will also increase. And we see this quantitatively through Henry's law, which is the concentrated of a dissolved gas is equal to K, which is just some value, times the partial pressure of that gas above the liquid. Okay, so definitely remember Henry's law. Concentration and pressure are directly proportional. But I met with a student during office hours, and this is something that I think is pretty important to bring up. Realize that the concentration of dissolved gas is for a single gas, right? And same with the partial pressure. It's of a single gas. I think it was actually a homework problem with a diver going underwater, something like that. But realize, right, let's say we have a can of Coca-Cola, right? And there's a certain amount of CO2 dissolved in it. Now realize that that's directly proportional to the partial pressure of CO2, okay? It's not necessarily directly proportional to overall pressure, right? So maybe the can's sitting on your counter and the pressure in your kitchen might be 1 atmosphere, but the partial pressure of CO2 gas in your kitchen would probably be much smaller than 1 atmosphere. It might be, let's just call it 0.001 atmospheres. Okay, so just remember that it's the partial pressure of the gas that's dissolved, if that makes sense to people. And then lastly, temperature does play a role in solubility. Solids typically increase in solubility as temperature increases. I'm sorry, this last bullet point is wrong. This is supposed to say solubility of gases generally decreases as temperature increases. These are both supposed to say as the temperature increases. So I do apologize for that. So solids will increase with temperature while gases decrease as temperature increases. Okay. Are there any questions on these 2 points before going into our colligative properties real quick? Okay. Perfect. And if there are, again, feel free to unmute your microphone or throw it in the chat at any point. So colligative properties. So just remember that these are properties that depend on the concentration of solute particles, not really their identities themselves, right? So don't care about if it has a positive or negative charge or really what that charge even is. It just cares about what's the molarity-molality of it. And then also, does this compound split into multiple ions, right? Does it have a Van 't Hoff factor? Okay, so besides its ability to be an electrolyte or split into multiple ions and the molarity-molality, the actual compound itself doesn't really matter. Okay, and we have 4 colligative properties that we look at. We have vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Okay, and here are your equations for it, for these 4 colligative properties. Note that I wrote this equation in terms of boiling point, but the only difference between the boiling point elevation and freezing point depression equations is just that it would say delta TF for freezing instead of B for boiling, and KF for KB, which is a constant. Okay, and so for vapor pressure, basically PA will stand for the pressure created by our solvent in a solution, right? So that's for a solution, it's going to be equal to the mole fraction of our solvent times the pure vapor pressure of our solvent. Okay, I'd really just note that the mole fraction is of your solvent. I think some people do forget that because we're so used to talking about the solute. And so I would just say, remember not to forget that. That's probably the biggest misconception people have with this equation. Boiling point and freezing point, again, remember that they move towards the extremes. So compared to the pure solvent, a solution will have a higher boiling point and a lower freezing point. Okay, and then lastly, osmotic pressure. Pi stands for osmotic pressure, which is calculated in atmospheres. M is molarity, right? Big M, I would definitely note that freezing and boiling points have small m for molality. Osmotic pressures in terms of molarity, so definitely a big difference. R is a constant, and I saw somebody ask about that in the chat, and so I'll come back to that. T is our temperature in Kelvin, and I is our Van 't Hoff factor, right? We also see the Van 't Hoff factor in boiling and freezing point. We do not see it in our vapor pressure equation. And really, I, our Van 't Hoff factor, is just accounting for how many ions will our compound split into when it's added to the solvent. Okay, and does anybody have an answer in the chat for what R value do we use for osmotic pressure? Is it the 8.31 or 0.08206? Can anybody answer that? And can anybody say why they know that? Okay, this is definitely a skill, not just for this chapter, but for every chapter that you should be able to do. When you see R, you should, awesome, everyone's saying it, you should be able to use the units, or at least get comfortable using the units to evaluate, right? So osmotic pressure is going to be measured, it's a pressure, so it's going to be measured in atmospheres, right? So we want to look at the R constant that has ATM in it, right? Later on, and I'll show it when we get there, when we get to the Arrhenius equation, when we're dividing activation energy by R, right? Realize activation energy is going to be measured in kilojoules or joules, because that means energy, right? And so if activation energy is in joules and we're dividing it by R, that R should also be in terms of energy. And so that's how we know that when we're using the Arrhenius equation, it's the 8.31. So yes, great job, everyone. Definitely use your units to help you figure that out, because it definitely is kind of difficult to keep which R's are which without looking at the overall context of the equation. Okay, just some random other notes. And again, these are just some things. There are other important things from this chapter, but vapor pressure, right? We have two types of solutes or compounds. We have something that we call non-volatile solutes or compounds, and these do not exert their own vapor pressure, right? Basically, they only affect the colligative property of vapor pressure lowering by decreasing the mole fraction of our solvent, right? So you just use the normal Raoult's law, which is our vapor pressure lowering equation, when a non-volatile solute is added. Okay, now a volatile solute or compound makes it a little bit harder, these problems, right? Volatile solutes or compounds do exert a vapor pressure, okay? And so we have to account for them in Raoult's law. So let's say we have two compounds that are volatile, and they're both liquids, so they each have their own vapor pressure, and we'll call them solvent A and solvent B. And so the P of our solution, right, the total pressure above our solution, will be equal to the vapor pressure of gas A plus the vapor pressure of gas B, right? And we basically do Raoult's law for each one of these partial pressures individually, right? So the partial pressure of A is equal to the mole fraction of A times the pure vapor pressure of A plus the partial pressure of compound B, which is equal to the mole fraction of B times the partial pressure of the pure solvent B, right? So that's kind of how you do it if you have multiple volatile solutes. Okay, lastly, osmotic, kind of under osmotic pressure, we have something that we call reverse osmosis, okay? And so basically when we solve for osmotic pressure, we're solving for how much pressure is required to stop osmosis. Okay, and so reverse osmosis occurs when we apply an external force or pressure, and that pressure is greater than our osmotic pressure. Okay, when the external pressure is greater than the osmotic pressure, reverse osmosis occurs. Okay, and reverse osmosis is quite literally what it sounds like. It's just the opposite of what we see during osmosis. Okay, and so during reverse osmosis, we see the solvent flowing from areas of higher solute concentration to lower solute concentration. Okay, again, there are other things that are important. I would definitely study ion pairing. You should definitely be familiar with hypo, hyper, and isotonic and what those terms mean. So again, there definitely is other topics, but I just wanted to touch upon the main ones. Are there any questions on chapter 11 before we kind of quickly go through chapter 12? No, electrolyte and volatile do not mean the same thing at all. Volatile is referring to vapor pressure. So volatile versus non-volatile is, does it create a vapor pressure or not? Electrolyte means when you add it to the solution, does it split into ions, right? And when something splits into ions, it's called an electrolyte. And when things split into ions, they conduct electricity, right? That's kind of where electrolyte comes from. Okay, so electrolyte, non-electrolyte is talking about your Van't Hoff factor Volatile, non-volatile is referring to our vapor pressure, and it just means, does it contribute its own vapor pressure or not? Okay, and yeah. Okay. So chapter 12, we're going to talk about rates and relative rates. We'll kind of very quickly go through the rate law and solving for that. I think we kind of talked about that a bunch already though, so I think people are probably pretty okay with that. We'll talk about the integrated rate laws, and then kind of our energy portion of this chapter, catalysis, activation, energy, Arrhenius. Okay, so rates and relative rates. Okay, so whenever you can, use just your simple rate formula, right? So the rate of appearance or disappearance of compound X is equal to the change in concentration of X divided by the change in time. Okay, if it has a negative rate, it means that it's a reactant, so it's disappearing over time. Well, if a positive rate indicates that it's appearing as time goes on. Okay, and again, you use this formula whenever possible. Okay, now you use this formula or this general setup, relative rates, when let's say they give you information about compound B, but they ask you for the rate of compound A. Okay, so when you're given information about one compound and asked about another, that's when you use your coefficients and do this relative rate. Okay, and again, negative means it's a reactant, positive product. Okay, this is the generic formula for rate law, right? So rate, the units for rate are always going to be molar per time, right? Time can be any amount of time, but you know, seconds, days, hours, whatever. It just depends on the problem, and that's going to be equal to K, our rate constant, times our reactants raised to whatever order they are, right? We have to experimentally solve for these orders. And remember that K can change. K can change in value and in units. Okay, and so you have to evaluate what our overall reaction order is to find K.
Could you go back to the slide before that one so I could just take a quick picture?
Okay.
Thank you.
Yeah. So this is the generic steps to solve. If you're given a chart and asked to solve for the reaction order, these are kind of describes the steps you can take. I'm sure by now you're familiar with it. And it's kind of a good studying technique to not have these steps and almost solve a problem, look at how you did the work, and kind of write your own steps. You know, try to verbalize how you solved each problem. That can be beneficial. Okay, so I'm not really going to spend too much time on this. Novel trial, again, these steps sort of describe how to find the reaction order when you have to make a new trial. These steps are in terms of if you have two reactants, A and B. A, you know the reaction order for, B, you don't. Again, I'm not going to dwell too much on this. This is just a resource that if it helps you, great. If it doesn't, perfectly fine to ignore. Now, this table is extremely important, and I highly recommend every student have it in front of them for the exam. You are given lots of these equations on your equation sheet, but they're not labeled, okay? And so because you guys have a huge benefit being able to have an open note exam, you know, having these notes, remember you have to print them off, no technology at all, but I would recommend every single person print this off or write it out for their exam, right? So it kind of describes 0, 1st, and 2nd order. And really the big key pieces of information we get from this table is our integrated rate law formula and our half-life reaction. So what are these? So half-life formulas, really you're solving for the time it takes for half of your reactant to disappear, right? So I'd say for your reaction to reach the halfway point. Really, it's how long until that reactant is halfway gone, okay? And so 1 half-life would be till it's 50% gone. 2 half-lives is half of what's remaining. So at that point, you've used 75%. Your third half-life would take you until you get rid of, what would that be, 87.5%, and so on and so forth. Okay, so that's what half-life is. Integrated rate law basically allows you to solve for what concentration do you have remaining after like a certain amount of time, or you can solve for how much time it took for a certain amount of concentration to be remaining. Okay. And if you ever see A naught, like this A with a 0, that means initial concentration or your concentration at time 0, right? Basically the same thing. Okay, I think there's just 2 more slides of info. So activation energy, again, remember that this is the energy required to convert reactants into products. It's the difference in energy state between the transition state and reactants. Okay, and if we have enough energy, right, if our energy is greater than the activation energy, then we will convert to products. But if we don't have enough energy, the reactants will go back to their original form, right? It is possible for reactants not to have enough energy to overcome this energy barrier that we refer to as activation energy. Now, catalysts, we can add catalysts to speed up reactions, and they do so by lowering the activation energy. Okay, so they lower that energy barrier. And by lowering it, it makes it easier. And we'll talk about it a little bit more on the next slide when we talk about collision theory. I would definitely remember it comes up very often in a multiple choice question that catalysts aren't used up in a reaction, right? So they're not used. And there's 0 order, meaning if you change their concentration, it doesn't change the rate of reaction. Okay, those are, again, these theoretical points about catalysts almost come up every year and in one multiple choice question. So definitely note these things. Okay, and this is, I think, the last slide before I'm happy to answer any questions on really anything relating to this, but it's collision theory in our Arrhenius equation. Oh, and I spelled theory wrong here, so I apologize. Roy. So collision theory, basically it describes the factors that cause K, that rate constant, to be what it is, right? So our rate constant is kind of the combination of our P factor, which P basically stands for orientation, right? Is the orientation between our reactants right for this reaction to occur? It also is dependent upon Z, which stands for frequency. So how often do my reactants collide together? And lastly, it also depends on F, which stands for collision energy. Basically, F stands for like what fraction or what percentage of my collisions have enough energy for me to actually overcome that activation energy and become product, right? So let's say 1 out of 10 collisions has enough energy to overcome the activation energy. Then our F factor would be 0.1, meaning 1 out of 10 has that energy. Okay, we have our Arrhenius equation, right? So this basically describes collision theory in just something that we can calculate more, right? So K is still our rate constant. A is our frequency factor, and it's the combination of this orientation portion along with this collision frequency portion, right? So our frequency factor accounts for P and Z. And then the E raised to the negative activation energy over RT is our quantitative way to express F, the collision energy. Basically, how many of our collisions actually have the energy to overcome our activation energy. Okay? And if we take the natural log of this entire equation, we get the natural log of K equals natural log of A minus EA over RT. Okay, now you can actually graphically show this. So our y-axis could be natural log of K, our x-axis could be 1 over T, and when you do that, your y-intercept is ln A, and your slope will be negative activation energy over R. So be wary of that. Graphical forms of this can come up. Also realize that this second equation you'll very much use if you have a catalysis problem, right? That first problem we went over, you'll often use this equation to solve for activation energy in those catalysis problems. Lastly, we have this equation that I just call the CC equation because I would butcher it if I tried to say it. And basically, this allows us to see what the different rate constants are at two different temperatures, right? So typically, you'll be given three, or like you might be given of the Ks and the temperatures, you're typically given three of those variables and asked to solve for the fourth, right? So you might be solving for T2, T1, K2, or K1. They also could have you evaluate it for activation energy. You should, again, be very familiar with this equation from your lab sections, from hopefully practice up to this point, but you should definitely expect to see this at some point on the exam. Okay, and that's all I have for review material, so I'm happy to answer any questions from here. And again, just a reminder, I will, after this is done, be finishing up the last couple problems that I have to, making sure that they work out, and then I will be recording me going through those problems, and I'll be posting that later tonight. Okay, but I won't be showing the challenge problems until then, just because I want to make sure that there aren't issues, or if there are issues, I mitigate them as much as possible. So the question that was asked in the chat, in case you can't see it, says, are radioactive isotopes half-life always first order? We had one on the practice exam where we had to assume it was first order. No, I would say no, that they're not always first order. But if they truly give you no way to know what order it is, I would assume it's first order. And I would say that assumption for any problem, whether it's radioactive isotope or not. However, especially on an actual exam, they should give you some indication as to what order it is. Okay, so you shouldn't be put in the situation where they don't give you some way to figure out the reaction order, but if they don't, I would assume it's first order, especially if they ask you how long does it take for blank to be left, and if that blank is a fraction, I would expect it even more to be a first order reaction. Okay, so if they say how long would it take for 1/200th of the original concentration to be remaining, I would very much expect that to be a first order reaction. But I wouldn't say that you can automatically assume that. Yeah, no problem. Any other questions? Okay. I'm not sure if other questions are coming, so I'm just going to end the recording here, but I will stick around if people do have questions or want me to go back into the PowerPoint.